Hey everybody, this is Larry. This is day 24 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know how you think about today's problem. And this is loading. Is it just my computer? But yeah, the contest is in like 2 hours, so this will be a good warm-up, good practice a little bit before that. We'll see how that goes, but I might even sleep through it, but okay, things are still loading. Okay, let's go. Okay. The title seems to be count complete tree nodes from the URL, but things are still loading. Okay, today's problem is 222 count complete tree nodes. I also want to say that, join me on Discord, hit the like button, hit the subscribe button. I did say that already. But yeah, I think a lot of people have been just on Discord nowadays, so they don't even, I don't know. They clearly have not watched my videos because they talk about stuff that I was like, I addressed this. But anyway, while you're here, I hope you enjoyed this video though. Okay, given the root of a complete binary tree, return the number of nodes in the tree. Okay. Every level except for the last is completely filled in a binary tree. Okay. Yeah, I was gonna say, if you can do an O of n, I mean, I think that's just like do a depth first search or breadth first search or any traversal. You could count the number of nodes and it'll be O of n, right? Let's see. I think how do you do it in faster than O of n? I mean, I'm trying to think about an invariant that I could try to abuse. So one thing to note is that if we keep on going right, that will give us the height of the tree, maybe plus one, or actually mostly plus one. So then now we try to figure out, now we are trying to figure out on the last level then what is the thing that's blocking it, right? And I'm trying to think whether there's a good way of saying that. So there is this thing where there's I'm trying to figure out the common cases, right? So there's this one, the example one, but there's also one that's just, for example, the same thing, but 5 nodes, right? 5 nodes then has a different thing because now 3 has 3 has no children, but 2 does, right? So, I guess you can also, given the height, what can you do, right? So now let's say we know the height because we just go all the way to the right, and see if it's complete or whatever. Let's say we're given the height. What can we do? Can we do a binary search on that? Because then, let's see. What is the complexity there, right? So you have O of h to figure out the height. That's not bad because h is, of course, h is equal to log n. So this is just equal to O of log n, roughly. Or, for a complete tree, right? And then now we do a binary search on the last row. Well, the last row will contain n over 2 nodes, which is going to be n over 2 nodes on the last level. And then we binary search on it. So binary search is going to log n. So there's going to be log n iteration, each costing log n time, because it takes the height of the tree to go through. So then this means that iterations to find the last number, and each iteration costs O of h or O of log n time. So total complexity is O of log square n, right? Is that good? That's clearly faster than O of n, but is that going to be the fastest, or like, is it good enough? trying to think really quick. Because I think, yeah, I mean, I think all the other ones that I have is linear because it just end up traversing mostly the tree anyway. So I think the binary search is needed to get it down, and I think this is okay, maybe. Let's see. I mean, I think we can implement this now. So yeah, let's what is this? Okay. Wait, is node dot value? I'm just trying to see where they always throw it from 1 to x, but it seems like it could just be random number. Might not even be unique, which is fine. It doesn't change the way that we care about it. But I'm gonna just try to play around with this one just to see if they just to see if this is a valid input. It seems like it's okay. So it seems like it's valid input and is expected 6. So, okay, so we don't care about the value anyway. But I thought it was just interesting then. Okay. So yeah, let's find out the height. Let's start by figuring out the height. Or this is height of the rightmost node. And what this means is that on the h+1 level, it will have on h+1 level, it will have 0 to roughly O of n nodes, maybe. We'll do the math depending on the height, of course. I think it's maybe like, if the height is 4, I mean, we could do the math. Let's figure it out for a second. Okay, that's, yeah. Height is equal to 0, node current is equal to root, and then let's actually wrap this in a get height thing. Okay, so while current dot right is not none, current is equal to current dot right, height, and of course this actually starts at 1 because we count at the root, and the root is 1 height. I think this is right. Okay, and if current that this is return height, so this is actually the height of the last completed level. So the number of nodes will be on the h+1 level, and h+1 level will have, let's see, on the first height is 1, so okay. So it should be, because we're 1 indexed in this case, the second level would have 2. Okay, so it should be 2 to the h+1 minus 1 nodes. So of course that is just 2 to the h. So okay, height is equal to get height. Yeah, we get left is equal to 2 to the h. I'm writing it this way for the benefit of the viewers at home, but yeah, and then right is equal to power of 2. This is just me setting up binary search. Plus 1 minus 1, right? Am I right? This is the number of nodes on that height, but I think I messed up here, maybe, because 0, 1, 2, 3, 4, 5, 6. What? 0, 1, 2, 3, 4, 5, 6. But so it has 3 nodes. So 1 node, 3 nodes. So then here 0, 1, 2. So it will be 3, 4, 5, 6. How do I want to count this? Maybe I'm just using weird math. Okay, give me a second. Let me think about this for a second. This is medium. I mean, this is doable. It's just I'm doing it really funkily. So the last completed height is h, height, right? That means that there are this plus 1 minus 1 number of nodes, then plus 1 would be the next next node number, and then this would be the next node number, I think. Let's double check this real quick. So for 6, I would expect 3 and 7, 3, 4, 5, 3 and 6. That's not right. Oh, because wood can be empty. Wood can be empty is a little bit silly, but okay, fine. I mean, we can also hack it, or we can fix it, but I think this is fine. Okay. So for 1, 2, 3, 4, 5, 6, I think I did something really wrong here. So this returns 1. Then the next node should be, did I have an off by 1? Maybe I have an off by 1 then. Oh wait, well this other thing is just really wrong. Maybe. So that's what I would also advocate, is just sanity checking your stuff, right? Because you need to always sanity check your stuff. Okay, so this is fine. It's just that we're one base now, so it's gonna be 1, 2, 3, 4, 5, 6, 7, right? Yeah. Because basically, if you wait until the end to kind of check, that's when you have debugging. So what I like to do is, when I have some questions, or if I doubt myself a little bit on the house, I will test myself before, and just to kind of make sure that this is what I believe it is, and now it is. Okay. And then now, so we binary search from 4 and 7, right? So, okay, so this is just standard binary search stuff. While left, whoops. Mid is equal to left plus right over 2. Are there mid nodes? If good of mid. So if there are mid nodes, then we want to be inclusive. So if, then we will set left is equal to mid. Else, the right is equal to, wait. So if it's not good, then we have fewer nodes where mid is not good. So okay, so I have to do this. Okay, that makes sense. And left. And then now we just have to implement the good function. So the good of x, so are there x nodes in the tree? And we can do that by looking at each bit. Yeah. Yeah, this is a little bit annoying to do, to re-index in a correct way, but they all have height labels, so I think we can just do for the math is a little bit tricky, because basically for given height you go left and right depending on whatever, right? So yeah, so current is equal to root. So for I in range of height, if current something like this, maybe I think I'm off by 1 though, but then current is equal to current dot left, else oops. Current dot right, and I think we can do this -1. Basically, if current mod 2 is equal to 0, then that means that we're going left. Return current dot left is not none. Otherwise, we just return like something like this, but I think I might be off by 1. This should be maybe -1 more, but I'm not sure. Let's check it real quick. This is a terrible way to check it though. But oh yeah, this should be X for the input X. I don't know why I put current there. Just confusing, I think. Yeah. Okay, this is the wrong answer, but that's fine. Okay, but we did get the 6 correct, but the 1 no. Oh, okay. But that's from me actually. I was focusing on getting the numbers right on that row, but actually there's one more possibility, which is that there's the last thing is complete, right? So actually, if I, for example, if I do something like I expect this to be wrong too. That this should give me 4 or 7. Actually, oh, 8, sorry. Yeah, because it thinks that this is, yeah, so it doesn't have the possible thing, but I think that should fix it. Oh, maybe not then. Why doesn't this fix it? So now this is, thinks this is 4. Oh, because this number doesn't have that height. Okay. So the reason why this is wrong right now is because it thinks that on my bound on my left right on the binary search, the left bound has to include at least 1 node. So it does this thing, but we don't take account the case where there is no node right to the left, and it is already a completed tree. We can actually just add that real quick. There are a couple of ways to do it, so that's why I didn't think about it. But yeah, let's see. Is there height? Is there a node of height plus 1? Right, by going to right, by going to left, whatever times, right? If it's not none, current equals current dot left. This may be off by 1 again, but current, oh, else return. So that means that the height is complete. So then we can just do power of 2 height -1. I think this is good, maybe, but I may be off by 1 again because I'm not really, honestly, I'm not being very careful today about that. So yeah, so now this should be good. Let me know if that was confusing actually. So basically what happens is that height, and we choose an inclusive bound, right? We choose the left bound to, because our assumption is that there is, for this bound, and it's not very easy to fix in this context of, we know that there will be at least 1 node on that height, and the reason why is because this function depends on the fact that there are height. There is at least 1 node in this height, particularly this part. So when that doesn't exist, that makes it a little bit awkward. Let's actually just try like very obvious small examples before we submit. Also, the good part about this is that you can write, you can write a very easy linear checker, just to kind of convince yourself if, in case you do feel like you're running into issues. Oh, I do have a wrong answer somewhere. Why is this? Dong dong dong, off by 1. Dong dong dong, probably off by 1, but. And this is why we test things. But let's see. If I just messed up something completely. Huh. Do I just not know how to count after 8? Is that right? That's weird. Okay. Let's do a couple more just to see if I can actually did not expect that. So maybe there's some weird typo somewhere or something. So, huh. Man, I'm having a lot of issues with this one, even though it's only a medium. Let's see. Okay, so it thinks that there's at least 3 completed height, which is true, because it goes up to 8. Yeah, it goes up to 7 nodes. But then so it tries to binary search on 8 and 15, and then but then it does it incorrectly because it cannot find the 9th node. This always look a little bit awkward. I don't think fixing this would do it, because I think this skips the last one. I think that's why. But maybe I'm wrong on that one. Okay, maybe I am wrong on that one. That one, I mean, so the reason why I knew this is because I always thought this was off by 1, because it doesn't make sense that if I is 0, this is height. But I was okay. The thing that surprised me also is that it did work correctly for a lot of examples, just not these ones. But this is why you test, I suppose, and this is why you test the obvious things. And I would have caught that anyway, even if they didn't give me the answer, because, well, you know the answer to this one, and you can, even if you didn't, you can add a verifier type thing. But yeah, okay, it looks okay now. Maybe add one more, just because there's one more level. I think maybe 16 is already another level actually. But okay, so let's give it a submit, and hopefully that's good. Oh, I have done this before. I don't remember this one though. Hopefully I'm good this time. I'm a little bit faster this time. What did I do last time? I don't remember this one though. I would have thought I remembered this, but maybe I'm wrong. So I do get the depth of the what am I doing last time? Wow, this is definitely a funky. Oh, let me explain this album first, and then we'll talk about the other one maybe. Well, because I don't want to kind of confuse people at home. But yeah, but basically the idea here is that we. Okay, and this is maybe I'll bring up Paint for a second. Wow, 23 minutes. This is a slow one for me. But yeah, just going over the explanation. If you're still around, usually I say in the beginning that, you know, yeah, in the beginning that I usually say that I'm solving these live, so it may go a little bit slow and fast forward. Because every time I don't say it and then it goes long, people complain that it goes too long, and I forgot about it this time. So, oh well. It is what it is. Oops. I'm lazy, so I'm just trying to copy and paste this. Okay, so you have something like this, right? And the idea is that by going all the way down the right side, you're going to get roughly, whoops. By going to the right side, you're going to get either H or H plus 1, right? And here, we know that there is going to be, like, we know exactly how many nodes there are because this is just binary tree stuff. So then we just have to do a binary search on each one, like, hey, does this have that many nodes, and so forth, right? So that's basically the idea here. Oh, I didn't, I was drawing stuff, but I didn't put it on screen. Okay, well, this is what I was talking about. So basically you go down the right side because, yeah, and then they'll give you a number H for the number of height. And then on the height plus 1 level, you can do a binary search on counting, you know, whatever. And the cost of that is just going down the tree. So it's going to be O of H. So yeah, So in this case, as you can see, wait, did I mess my analysis up? Oh no, because I was gonna say, and we can analyze it in a number of ways. I think we kind of already did earlier, because otherwise we wouldn't have done it. But basically, yeah, you could have done it this way, which is that the O of n nodes in the last level, specifically n over 2, right? Because half the nodes are on the last level at most, so it takes log n iterations to find the last number, and each iteration takes O of h or O of log n, and so the total complexity of log square n, right? So that's gonna be fast. Yeah. That's all I really have for this one. For space, we actually don't do any recursion. Oh wait, no, this isn't recursion. So we're gonna, in space we actually use constant space because we use while loops, and therefore there's no stack space, so it's just gonna be O of 1. So that's pretty cool. But yeah, let me look at my older solution. Don't remember this one. So basically, I look at the depth of the left, and then the depth of the right. If they're equal, then oh, I see what I'm doing here. So if they're equal, then that means that what is the complexity of this now? I mean, I probably have a video on this where I analyze this a little bit better, but is this better than linear time? I mean, it is faster than this is faster than looking at every node, but is it better than O of n, right? Those are two different things. So if they're the same, we go to the right. So that means that every time we do this recursion, we get rid of half the nodes, right? So that means that we do this recursion log n time, right? Because every time we do this recursion, we only look at we get rid of half the tree, right? So this is going to be log n, and then every time we do this recursion, we calculate the depth, which is O of h, which is also log n, as we said. So this is going to be log square n as well. Older Larry is smart. I don't. This is a way tricky algorithm to get if you ask me, because that requires a lot of understanding of the invariant of the structure of the binary tree. Because I mean, if you watch enough these videos, you'll see that I do the exact same thing very often, but this time I did not, obviously. So it's kind of always curious to me. And also one more thing is that we do actually cache the answer for each node, but even if we didn't, it would be log square n. I don't know if that caching gets rid of anything other than, I mean, it definitely makes it faster, but I don't know if it makes it complexity faster by that much more. But yeah. Anyway, I mean, I think this is log square n as well. Let me know if you disagree. But this one has O of h space because we're doing some recursion thing, and yeah, and it takes O of h recursive step. But oh well. So yeah, well, this one is O of 1 space, I think. Let me know if I missed something and I'm wrong. But yeah, that's all I have for this one. Let me know what you think. Hit the like button and subscribe and join me on Discord. We're going to do the contest later today, so I hope you join me for that. Stay good, stay healthy, to good mental health. I'll see you later. Bye-bye.